All right, so hopefully you all had a good break and are ready to get back into things. So just recall that we're kind of just wrapping up a couple of small topics at the end of the course. We're running a little bit ahead of schedule probably. So today's plan is to talk about volumes a little bit, mainly focusing on section 6.2, but we might actually touch a little bit on section 6.3, just depending on how much time we have left at the end of 6.2. Wednesday discussing an integration technique, integration by parts. So we saw the substitution rule, which is kind of the counterpart to the chain rule. It's the integration counterpart to the derivative chain rule. And integration by parts is kind of the integration counterpart to the derivatives product rule. So we'll take a look at that on Wednesday. And then next Monday, so a week from today, we'll actually just use that as a reading day. So the sample final exam will be available. So use that day to kind of review the sample final, prep for the exam. If you have any questions, shoot me an email. I'm happy to, if anybody wants to meet during that time, I'm happy to meet during the standard class time on Monday if you have any last minute questions or anything. But I didn't want to cover anything new on Monday because the final exam week, we're running from Friday to Friday. So Friday the 6th, this coming Friday, in a few days, the exam will open, the final exam, and it'll be open through Friday the 13th at midnight or 11:59 p.m. Friday the 6th, it'll be available at 9 a.m. So this way, you have a little more flexibility. If you want to take the weekend to do the exam, you're certainly welcome to do that. If you'd rather wait a little bit and take it during final exam week, that's fine too. I would strongly recommend planning to take the exam no later than, say, Wednesday afternoon or evening. And that way, just in case anything goes wrong, that gives you a business day or two to kind of get things sorted out, reach out to me, us figure out a solution if there's a tech issue or anything like that that comes up. Uh, the Friday the 13th at 11:59 p.m. is a hard deadline, so that's not available to be pushed back. So make sure that don't wait until the last day or even 2 days to take such an important exam. And it is comprehensive. It covers chapters 2 through 5 and section 6.1. And there will be a bonus problem from section 7.1. So sections 6.2 and 7.1 won't be properly on the exam, but just a bonus from 7.1. So 6.2 and 7.1, as I've mentioned before, are kind of, in that area where we're looking a little bit ahead to Calculus 2. And when you take Calc 2, we'll pick up probably, in the middle of Chapter 5 with some review of Chapter 5 and 6.1, and then kind of start the Calc 2 material in 6.2. So there's a little bit of an overlap there to ease the transition between the two courses. Any questions on any of that? I know that's a lot of administrative stuff, but I like to do the rundown each class at this point in the semester just because I know that you've got, several classes and life and complicated things that you're probably juggling. So kind of uh, keeps everything in perspective. Okay. And the quote of the day today is from a friend of mine who lives in St. Louis named Mark. He works in the finance field. He's a CFA, a chartered financial analyst. And we were just chatting one day, and he said that this is like one of the principles that he lives by as far as business contracts go. 10 times out of 10, I take a questionable contract with a solid person over an ironclad contract with a questionable person. And personally, I've seen this pop up quite a few times, dealing with whether it's contractors, doing like HVAC or electrical plumbing kind of stuff. Um, it's more about who's actually doing the work than the legality of the contract, right? I mean, if you get to the point where you're trying to sue somebody for breach of contract, that's already a failed enterprise all along on both sides of the contract. So, um, be the kind of person that somebody would take a handshake agreement from, and deal with people that you would be comfortable taking a handshake agreement from them. So I think that's the the principle here. And the more important something is to be done right, the more important it is to follow that principle, at least from the experiences that I've had. I think that that's true. All right, so moving on to section 6.2. So we're working on applications of integration, and last time, uh, seems like forever ago, it was about a week and a half ago, I suppose. Um, we saw using integration to find the area between curves. So maybe just a super quick review of that. If we have two curves, f and g, with say f bigger than g, and if I want to find the area between them, say from A to B, call this area A, integral A to B of f of x minus g of x dx. And this is if f bigger than equal to g. We don't have to worry about signed area in this case because we're always taking bigger minus smaller. So the sign of that difference is always positive. So even if, say, f and g were both down here below the x-axis, this is still a proper area because the difference is always bigger minus smaller, that's always positive. Right. So this is always, well, I suppose non-negative. Okay, so let's look at finding volumes using the disk or wafer or washer method. Um, I had pulled up a video that I wanted to show, and of course it was with it being a week and a half ago, I only remembered right now and didn't remember to pull it up before. But so has anybody ever done or seen those? I I don't know whether you call them a puzzle or like a sculpture, but they had these like sculpture kind of things, at least when I was younger, that was like a stand with maybe a post in the middle, and you would open up this box, you'd put the post on the stand, and there would be all of these just flat, basically wafers, like essentially a piece of cardboard that was cut out and that had a slit in the middle. So all of these different ones like this, and you would stack them up, with that slit going over that pole. And what they would do is they would eventually make, say, a 3D sculpture. So it might be like a head of, somebody famous, or, an animal or something like that. Um, so if you look up something like 3D sculpture puzzle or something on YouTube, you'll see an example of this if it's not ringing a bell. And that's really what we're kind of imagining here. So our definition is let S be a solid that lies between x equals a and x equals b. And yeah, so here I have x and I have some solid. I'm going to draw a sphere because it's easy to draw, but it could be any kind of solid. And if we consider the cross-sectional area in plane PX is a plane that is perpendicular to the x-axis. So I think of plane PX being like this. So it's a plane perpendicular to the x-axis that intersects the x-axis at some point. We'll just call it x. Now we note that this plane is going to intersect this solid with some boundary, maybe like this. So that might be the cross section of that solid, this sphere, this ball really, in this plane. So when I cut this solid with this plane, this green curve will be the cross section of that solid in that plane through that point X. And so we can see it a little better. I can bring that plane out here just so that we're looking at it straight on. And we see in this case, our green cross section of the boundary is going to be a circle. And this it's going to be basically filled in, right? Because we're cutting through a solid. So it's going to be filled in, but typically I'm not going to draw it as filled in. So the cross-sectional area in plane PX perpendicular to the x-axis is denoted A of x. This cross-sectional area, the interior of this green boundary curve, is denoted A of x. It's an area because it's a two-dimensional object. And it's A of x because it's dependent on which x I choose, right? If I chose a cross section over here, I would get a different green curve and a different area. So depending on where I choose to place my plane, still perpendicular to the x-axis, but I can move it left or right, I would get a different cross-sectional figure and a different cross-sectional area. Then we say that the volume of S is the following. Well, basically, I could kind of build up approximations to this figure in kind of a Riemann type way. Let's see if I can actually draw this. This might be close to the limit of my artistic skills, but I could think of having a little chunk of cylinder there, and then another chunk of cylinder that's a little bigger kind of next to it, and then another slightly bigger bit of cylinder. Now it's starting to look kind of messy, but so I have these little cylindrical pieces that are getting bigger on that side, and then on the other side, maybe I'll switch colors so we can differentiate between the two sides. So there is a piece of cylinder. And then a smaller one kind of stacked next to it. And so on. So we can see that this kind of approximates a sphere with whatever it is, 5 or 6 cross-sectional volumes, so to speak. And if I use more and more of these types of volumes, then I get a better and better approximation to that sphere. What is the volume of one of these? Well, it's the two-dimensional cross-sectional area, A of x, times basically the height of that cylinder, which we can call delta x. Right, this has a very Riemannian feel to it. This A of xi delta x is kind of like a V sub I, the volume of the ith little cylinder here. I add all those up, that gives me an approximation to the volume of the sphere. When I'm using, 5 or 6 cylinders, it's not a very good approximation, but I can increase the number of cylinders I use. Delta x decreases. So I'm using more and more cylinders of smaller and smaller width or height or however you want to think about them. And that's giving me a better and better approximation to the continuous volume. And in fact, in that limit, we end up with just the integral from A to B of the cross-sectional area. So of these infinitesimal volumes, these slices of 0 thickness, infinitely many of them stacked up, that's what we're working our way towards as we take the limit here. So let's compute the volume of a sphere of radius r. So again, I have my sphere here. And if I wanted to be really technical, I suppose I'm calculating the volume of a ball with radius r. Technically, a sphere is the two-dimensional boundary surface, but we can think of the volume of the region enclosed by a sphere with radius r. I'm going to choose the sphere centered at the origin. Well, why not? No reason to make it more difficult than it needs to be. So coming out here on the x-axis, to the rightmost point is going to be at r, and the leftmost point at negative r. I have my plane perpendicular to x, px. That plane is going to cut this volume, and it's going to yield a cross-sectional area like that. Let's bring this plane over here and look at it head on. So here's px. And there's a of x. I want to be really careful here. It might be tempting to try to make this a circle with radius r, but note that r is the radius of the sphere. We can clearly see if I pick a perpendicular plane really close to x equals r, I'm going to have a really tiny cross-sectional area here, right? And if I pick one right at the origin, then I'm going to have a circle of radius r. So, at that one instance, I might have a circle of radius r here, but generally speaking, I'm not going to have that. Okay, so how do I get this? How do I get this volume? Well, I do notice that the circular symmetry about the x-axis does mean that this is a circle, right? There's a rotational symmetry about the x-axis for the sphere. If I took a sphere and rotated it a little bit about the x-axis, it looks the same. So this is a circle. It's not just that it looks a bit like a circle in the picture, but it is indeed a circle. And what I really need is the radius of this circle. So for a given choice of x, well, I noticed that the radius of this circle is like the y value associated with a given choice of x. So kind of what I'm doing, let me scroll down. Oh, scroll down just a little bit here. Kind of what I'm doing is I'm taking this curve in 2 dimensions and I'm rotating it about the x-axis. So this is really a solid revolution. I'm revolving this curve about the x-axis, and that kind of like cuts out, in a sense, a volume that's a sphere. And if it goes from negative r to r, sphere of radius r. I know that this curve is the top half of x squared plus y squared equals r squared, or y equals square root of r squared minus x squared. So this blue height here, where I have a certain choice for x, and then I have this height, which is the radius of this green circle. That's this here. Trying to keep my colors all consistent here to keep things straight for you guys. I noticed that this point is x comma root r squared minus x squared. So again, when x is 0, my height is r, but most of the time my height is not r. So I don't want to just jump over here and make this a of x be a circle of radius r. That wouldn't be right. That would be like if we had a cylinder laying on its side. But here the cross-sectional radius is changing, even though the radius of the sphere is not changing. Okay, so the y coordinate here is the radius of the a of x circle. Or in other words, my a of x is, well, let me switch to green. My a of x is pi times the square of this radius, or pi y squared. You see the radius is just y. Or that's pi times square root of r squared minus x squared, or that is just pi r squared minus x squared. So that is my a of x. Okay, so I have that a of x. What do I do with it now? Well, that's really the hard part, because now I just plug it into the integral and perform the integration. I guess I should say the conceptually hard part, right? Sometimes performing an integral is difficult, but in this case, it won't be bad. I'm going to integrate over the relevant x values. Did I forget to write a negative r there? Yeah, negative r. Integrating from negative r to positive r, a of x dx, that's just our formula for the volume of the solid. This is going to give me pi times r squared x minus 1/3 x cubed. Kind of as a side note, if I look at this integral, I think I might have talked about street math before in this course, but I can never remember whether I mentioned it or not. But if you've heard it already, I apologize. But there's a professor from, I think he's from Harvard, but one of those like Harvard, MIT, Yale, something like that. And he published a book and I think has a mini course called Street Math. And it's like little ways to check your work to see if things seem to be on the right track or not. If I imagine that r, or radius, is like, say, measured in inches, and x would be measured in inches as well, I have square inches, square inches. This would be like square inches. Dx is in inches. I have square inches hitting inches. I have cubic inches. I have a volume. So I have cubic units of length. Two of those factors of units of length are coming from the r squared minus x squared, one from the dx. It seems like I'm on the right track. If I made a goofy flub or something and forgot to square this and I just ended up with pi square root of r squared minus x squared, I'd have like inches times inches. I'd be getting square inches for a volume. Something went wrong there. So just a little side note on that. So just as you're going along these problems, if you see a way that you can kind of check your progress and say, does this look right? That's usually a worthwhile thing to do. I see after my integral, I also have cubic inches or cubic units of length and cubic units of length. So everything still looks good. And evaluating this from negative r to r. I can make life a little easier for myself and come back here and use an integration property. I know that I'm integrating an even function. The only place I see an x, it's an x squared, so it squares off the negative sign over a symmetric interval. I can just make that twice the integral from 0 to r. That makes this a little easier to do. I don't have to, deal with a whole bunch of negative signs that I could easily mess up. 2 pi times r squared times r is r cubed minus 1/3 r cubed. And then minus the same thing at 0, but when I plug in x equals 0, that just goes away. So this is 2 pi times 2/3 r cubed. That is 4/3 pi r cubed. And we do see that that is the formula we might recognize as the volume of a sphere. Really the volume of the solid enclosed by a sphere. So 4/3 pi r cubed. That's what we expect. It does have cubic units. Things look right. Any questions on that one? Okay, so if S is a solid of revolution, if it's obtained by rotating or revolving a function y equals f of x about the x-axis, then a of x equals pi y squared, and our volume is simply integral a to b of pi y squared dx. That was what we saw up above here through all of these computations, right? We had a volume that was obtained as the interior of a volume of a region that's the interior of a surface that we obtain by rotating this function around the x-axis. That revolution property, revolving it around, will always yield a circular cross-sectional area, and the radius of that cross-sectional area will always be the height of the function at that value of x, which is of course just y. So that's where this all comes from. Okay, let's look at another example. Compute the volume of the solid obtained by rotating the region R about the x-axis, where R is the region in the first quadrant bounded by y squared equals 8x and x equals 2. So let's look at our region first. Typically, this is how we'll draw this. We'll look at the two-dimensional region first instead of here we kind of backed into the usual process, right? We backed into the two-dimensional region because we knew what a sphere looked like, but typically we'll be looking at our region first. So we have x equals 2. That's one boundary curve of our region. We have y squared equals 8x. So what? When x is 2, y squared is 16, y is 4. When x is 0, y is 0. And y equals square root of 8x. Uh, Having trouble getting my marker to work nicely there. Something like that. Not the prettiest square root function that I've ever drawn, but it is what it is. So this is my region, this bit in here. And we're rotating this about the x-axis. So what's my solid going to look like? Again, I'm going to try to do a good job of sticking with my same colors and roughly the same size of things here. And so my curve rotates around. Comes like this and back up the other side. So basically this looks a little bit like a bowl on its side. This kind of exterior bit here would be green, and this top surface would all be blue. So that top surface, that kind of almost like a plane there on the right at x equals 2, will be traced out by that blue line. And the kind of curvy bowl part will be traced out by the green curve. And then like the interior of the bowl would be, red if we were following this, or we were following the same color scheme. I'm gonna steal red because I need red for my plane. We have a formula now. We could trust the formula, but I think it's good to just get the geometric idea of this and really start to get this in our heads. Number one, because it's super helpful for Calc 3, just to have a little bit of practice imagining these three-dimensional objects. So looking ahead quite a ways, it's super helpful to have some practice there, but also just a lot of times being able to use both the algebraic side and the geometric side of a problem just is really helpful. So if you get stuck in one direction, you can jump to the other direction. So I have my plane perpendicular to the x-axis. There's px. I have a cross section. Suppose since I already used green, I'll draw the cross section in black maybe. And then if I pull this plane off to the side and look at it straight on, I have a cross section where the boundary is a circle. I can see the size of that circle, the radius of that circle is going to be dependent on x. If I pick x as close to 0, kind of far to the left, that's going to be a pretty small circle. If I pick them close to x equals 2, further to the right, that's going to be a bigger circle. and it's going to have it's going to be a circle of radius y. So a of x is going to be pi y squared, or we know the y squared equals 8x. It's going to be pi times 8x. And I see that I need to integrate from x equals 0 to x equals 2. So my volume is going to be integral 0 to 2 of the cross-sectional area of 8 pi x dx. This is my a of x. So here I have 8 pi. Integrating x gives me an x squared over 2. And just as an aside, I do have an odd function here, but it's not over a symmetric interval. So I can't really make use of symmetry in the way that I did above. But I have 4 pi times 2 squared is 4 minus 0 squared is 0, or that's 16 pi. So 16 pi, like maybe somewhere in the ballpark of about 50, something like that. So that's like about 50. And we could imagine that if we had a block, like a cuboid that we were carving this out of, we would need like a cuboid of size 8, so that I'd have a radius 4 up and 4 down by 8 by 2. 8 times 8 is 64, times 2 is 128. So this cuboid would have volume of 128. But we're cutting out quite a bit, right? Roughly speaking, over here, we're cutting out almost all of it. And over here, we're cutting out almost none of it. Or maybe not almost none. That might be a bit of an exaggeration, but much less. Can I imagine that, this number that's around 50, a little bigger than 50, is about a half of 128? Would I cut out about a half of this cube to make this bowl? That seems pretty reasonable, right? If you were telling me that the answer was like, 6 pi or something, if you were telling me the answer was like 20, that I have to cut out, 5/6 of the block to make the bowl, that wouldn't really look right, I'd want to check my work. Or if you were telling me I'd have to cut out like almost none of the bowl, that the answer is like 120-ish, I really doubt that I'd be able to only cut out, 8% of the block and make a bowl like this, right? So using some geometric intuition in this problem, maybe that gives us a little bit of a clue that, yeah, it seems like things are on roughly the right scale here, right? If I made a mistake where the answer is supposed to be 15 pi and I got 16 pi, I'm not going to catch a mistake like that. But if I got, 1.6 pi when I'm supposed to get 16 pi, or if I got, 100 pi when I'm supposed to get 16 pi, I would definitely catch a mistake like that. Um, so again, with that kind of street math idea, coming up with ways to quickly and efficiently check your work. Typically the more effort you put into a check, the more accurate it can be. But so there's a little bit of a balancing point there, right? And there are some problems that just aren't really easy to check in general. Any questions so far?
If you had something like an egg, like I'm guessing ellipse, you'd do this slightly differently. But if you had something like an egg, could you cheat and like top down view it and just do circles?
Yeah, so do we have an ellipse here? So an ellipse is actually a great example. Let's actually do an ellipse. Uh, yeah, good question though. We're going to see that an ellipse is actually quite similar to the sphere. An ellipse is just kind of like a stretched sphere, right? So let's say that I had a region that was elliptical, here I have x and y, and let's say it has it goes from negative a to a on the x coordinate and from negative b to b, or we'll just say 0 to b for this part on the y coordinate, and we're rotating this about the x-axis. So that region, I call this R, that region rotated about the x-axis will give me an egg, basically, right? An ellipse rotated around. I forget what they're called. It's either like a hyperbolic paraboloid or something like that. But yeah, so basically it's basically a squished circle is what an ellipse is, or the ellipsoid is kind of like a squished sphere or a stretched sphere, depending on how you want to think about it. So when I rotate this around, I'm going to have an upper bit. That's a bit of a flat ellipse. An upper bit and a lower bit. Like that. I'm going to have my cross-sectional plane. And I actually see that because of the fact that I'm rotating this way, not necessarily because of the rotational symmetry of the two-dimensional figure, the ellipse, but because of the fact that I'm rotating about the x-axis, that's what makes this cross-sectional area a circle. So even if this wasn't a nice ellipse in 2D, if it was some, wonky shape, even like this one up here, right? This didn't have nice rotational symmetry, but the ending solid had a nice rotational symmetry because it's a solid of revolution. So this will be a circle with a cross-sectional area a of x equals pi y squared. My ellipse over here, so I'm going to have x over a squared plus y over b squared equals 1. Why is that? Why does it work out that way? Well, when I choose x equals a, I want y to be 0. I know it's got to be something like a circle, right? It's got to be kind of like x squared plus y squared equals r squared, something along those lines. But when I have x equals a or x equals negative a, I want y to be 0. And when x is plus or minus a, x over a squared is 1. I've kind of used up all of the stuff that I have on the right-hand side, so this can only contribute a 0. So y has to be 0. And then likewise, when y is b, x has to be 0 because the y over b squared is 1, and I have 1 plus non-negative equals 1. This has to be 0 when y is b. So that's always how I think about it, rather than memorizing formulas. So then what is y? Well, I see that y over b squared is 1 minus x squared over a squared. We might end up with an integral here that, oh no, it'll actually work out. Okay. Or I have y squared is what? B squared times 1 minus x squared over a squared. So that's what y squared is. And that's just what I need up here. Yeah. Yeah, so really good question. And we see then the volume is the integral negative a to a of what? Pi b squared times 1 minus x squared over a squared dx. And we could even make this look a little nicer if we pull out a bunch of these constants, we do note that this is an even function we're integrating over a symmetric interval. So let's make this twice the integral from 0 to a. We can pull out a pi b squared, and we can pull out an over a squared, just to get the integrand looking a little nicer. This pi b squared all came out. And when this a squared comes out, I get a squared minus x squared dx on the integrand. So let me double check. I did a bunch of things in one step there. So I used the symmetry, made the lower bound of the integral 0 and put a 2 there. So that works. The pi b squared came out. The 1 over a squared came out and stuck an a squared there. So that should be right. And at this point, the reason I did that, I mean, in part it was to make the integral a little easier to do, but also to show the symmetry of this integral that we get here looks almost exactly like this integral that we get up here, right? Where just my radius is replaced by a. And I just have this correction bit in front here having to do with the b. So this gives me what? 2 pi b squared over a squared x minus 1/3 x cubed from 0 to a. So 2 pi b squared over a squared times a cubed minus 1/3 a cubed. So this gives me 2/3 times 2 is 4/3 pi. That looks familiar. B squared times a cubed over a squared is a. So 4/3 pi a b squared. Interestingly, so one thing we note is that if we have a equals b, we could just say equals r. If a equals b, we just have a circle, then we can just call both of them just the common radius r. We get 4/3 pi r cubed. We recover the volume of the region enclosed by a sphere in the event that we have kind of a degenerate ellipse that's just a sphere. So that's a good thing to check since an egg is or an ellipsoid is kind of like a squished sphere. We ought to, if we unsquish it, we ought to recover the same volume from the same formula for an unsquished sphere. The second interesting thing is that we actually see a bit of symmetry breaking here. Right, I have 2 factors of b and 1 factor of a. I mean, that kind of makes sense. Like I need 3 factors so that I get like cubic inches or whatever I'm using to measure it in. So that my units work out right. I need 3 factors, and I'm not going to make like 1.5 factors of each of them. That would be kind of strange. So because we're squishing in one direction and not the other direction, we have I guess, a different contribution in a sense from the B versus the A. There's no longer a symmetry in the sphere. Everything was nice and symmetric, but now we're like squishing in the B direction and stretching in the A direction, and we have a slightly different answer. We have a breaking of that symmetry. This doesn't look the same if I, flip it 90 degrees. The egg looks different if I do that. So, yeah, but yeah, good question though. I mean, yeah, like an ellipsoid like this or an egg shape could basically be treated the same way. We could have at the outset used, say, geometric arguments to even make this a little simpler. We could have said, well, I see the right side is going to clearly be a mirror image of the left side, and just at the outset started with that, just double the integral from 0 to a. That would have been a geometric way to make the same argument that we did in this step using an algebraic property of integrals. So instead of looking at this and saying, I recognize an even function integrated over a symmetric interval, I could have recognized a geometric shape that has some nice symmetry to it and leverage that at the beginning. So yeah, there's a lot of good points to be made in this problem. So yeah, thank you for bringing that up. Okay, so note that this region up here, we rotated about the x-axis. Here we have a pretty similar region. We want to compute the volume of the solid obtained by rotating this region about the y-axis in this case. So let's just highlight that so we don't forget. And like usual, let's start by drawing our region. It's the region bounded by x equals 0, y equals 3. X equals 0 is the y-axis. Y equals 3 up here. And x equals 2 root 10y. Or this would be like, if I square both sides, it's something like y equals x squared, right? So it's going to be a quadratic opening up. And I want to rotate this about the y-axis. I noticed that because I'm rotating about the y-axis and I would have nice symmetry over here as well, I'm really only interested in the first quadrant part of this region. Let me actually use black here because I've already used my other three colors. And we're rotating about the y-axis. Um, I've run out of colors, but I don't think we need any additional ones over here. All right, so if I'm rotating about the y-axis, I have a quadratic bit with a constant function top that rotates around to make a mirror image over here. And this looks a little bit like a bowl that is opening up. So again, my kind of blue boundary is representing the outer shell of this bowl. And that green straight line, when we rotate it around, that's kind of like the top surface of this bowl. It's like a filled in bowl. It's not like an empty bowl. And then the red line is kind of, because it's the axis of rotation, it's doesn't really contribute to the volume. So it's not like we're going to see any red volume in the middle here. And then like the interior of this solid bowl would be the black region. So the interior of this solid would be black. Now I notice here, if I just go on autopilot and say, okay, let me pick a plane perpendicular to x, px, I notice that let's see, black would be a good color to use here. I noticed that my cross-sectional area isn't super nice. In theory, there's nothing wrong with this. But my cross-sectional area looks like this, right? This top is y equals 3. And this bottom is like y equals, what would I have? If I square both sides, I get 4 times 10 is 40. It would be like 1/40th x squared. And then I would also have to integrate between two x bounds that I'd have to, figure out what they are. I don't think this would be the end of the world. I could say that this area is like some integral from here to here of 3 minus 1/40th x squared. But at the very least, we can tell that that finding this area using an integral is going to be a bit of a pain. And then having to integrate the result of that again, I mean, at best, this is going to be a pain to do. So hopefully I can undo all the way back to there. I might not be able to. Okay, so I don't want to use um, I don't want to use a cross section perpendicular to the x-axis. That worked out pretty well. But I'll use a trick that I saw in 6.1, which was it doesn't much matter which direction you tilt your head, so to speak. Right? We can use a cross section perpendicular to the y-axis instead. Because our axis of revolution or axis of rotation is the y-axis, this makes more sense. This gives us a cross-sectional area that is a circle. And if I bring this py down here, this plane perpendicular to y, cross-sectional area is going to be a circle because I rotated around the y-axis, so that forces it to be a circle, regardless of how nice or not nice this function is. This blue function over here. And furthermore, I know that the area, well, the area is going to be dependent on y here. If I choose a cross-section that's higher up, that's closer to y equals 3, I'm going to get a bigger area. That's lower down, closer to y equals 0, I'm going to get a smaller area. And I know that this is going to be pi times the square of the radius, and I see that the radius is just going to be the associated x value. So for this given y, I have an associated x value that is the radius. So it's going to be pi x squared. Be careful here, don't do something like this, integral 0 to 3 pi x squared dx, because these are y bounds, right? So don't jump ahead too quickly. Easy mistake to make because we see x and we think, oh, x is always the independent variable. Well, in this case, we're treating x as the dependent variable and y as the independent variable. So what is x squared? X squared is, well, 2 squared is 4 times 10 times y, 40y. Oh, pi times 40y. X is 2 times root 10y. So x squared is 2 squared or 4 times 10y, 40y. So my volume then is going to be the integral from a lower bound to an upper bound in y. So from y equals 0 up to y equals 3 of what? Of pi times 40y. And this is going to be dy. We're integrating along the y-axis. Or this gives me 40 pi times y squared over 2, evaluated from 0 to 3. Or this is 20 pi times 3 squared minus 0 squared is times 9. 180 pi for this volume. Any questions on this one? As a side note, we didn't actually ever have to find this point of intersection here. We never had to find, say, this x coordinate because we never used it. So not that it would have been the end of the world to find it, right? It would just been 2 square root of 10 times 3, 2 square root of 30. But we didn't have to find it. We knew that we started at y equals 0 and went up to y equals 3. So we did, in a sense, have to find this point of intersection, but that was an easy intersection to find anyway. Any questions so far? Okay, let's look at one more example here. Compute the volume of the solid obtained by rotating the region R about the x-axis. So we're back to x-axis, where R is bounded by these curves. And again, this one is going to be pretty similar to this one, except that we're rotating about the x-axis. So I know that y equals square root of x looks like this. So x equals square root of y basically looks like that, but flipped over the line y equals x. I know that, so that is this curve. I know that x equals 0 is the y-axis. And I have y equals 3 here. And that's my region. I'm rotating this region about the x-axis. So this is R, rotated about the x-axis. And you look at this and you say, okay, we've done this before. We've done 2 problems just like this, right? We have to be a little bit careful here, though. All right, so I have my exterior curve here at y equals 3. It's going to get rotated around down here to -3. So that's my green curve. My red boundary down here gets kind of rotated around to this side. So this, in some sense, this whole left face is going to be red colored. We can't see it, but if we, turn the figure around and look from the back, it would be red. This right edge over here is going to have like an indentation in it, right? It's this piece here is missing. So this almost reminds me a little bit of like a stadium or something where you have like, the Coliseum or something where you have the flat cylinder on the outside, and then on the inside, it kind of like slopes down towards the center. So it's a little bit like a stadium, like turned on its side. Obviously, these two, seats, so to speak, sides approximate. So it wouldn't be much of a stadium. There'd be no field in the middle, but I think you kind of get the idea. So we have something here that looks, maybe a little bit like kind of a bundt cake pan or something, or a bundt cake or something like that, a little bit. I rotate it about the x-axis. I'm going to choose to use a plane perpendicular to x. And here I notice, let me actually draw that plane a little bit better. Here I actually notice that I have an inner ring that's going to be formed by this inner blue piece of the cross section. So this red perpendicular plane cuts the blue curve. And it also cuts the green curve. If I pull this plane, let's go below so we can keep everything on screen. If I pull this plane out down here, I see I have an outer green curve. That's like the walls of the Coliseum, the outside of the stadium. And then I have an inner blue curve that's like the seats of a stadium, right? If you think of like, um, like a stadium and you took, if you were looking at it straight on and you took a horizontal slice of it, you'd be cutting through the outside, like cylindrical wall, but also through the inside of the seats. So the blue is like this where you're cutting through the seats, and the outside is like the green is like where you're cutting through the outside. The volume is what is between those two curves. So I've used up all of my colors, but we can go with this. So actually I'm looking for this cross-sectional area. So I have, let's say, radius little r for the blue circle. Blue and green are both circles because of the rotation about the x-axis. But I have a blue radius and I have a green radius. Maybe I'll call that capital R. And an area that depends on x, right? If I chose a different position for this perpendicular plane, I would get a different cross-section area. If I choose it near x equals 0, this inner radius is very small. The outer green radius always stays the same. And I have basically just a full circle. But if I go way off to the right, I have just a very thin boundary. This inner blue radius is almost the same as the outer green radius there. But this area is a function of x. I can see that. If I move the plane left or right, that area of this kind of washer, this is why it's also sometimes called the washer method, my area of this washer will change if I move my plane left or right. And I know that this is the area inside the green curve, pi big R squared, minus the area inside the little curve, pi little r squared. Or that's just pi times big R squared minus little r squared. Be a little careful. It's not like pi times the difference in radii squared. It's not pi times parentheses, big R minus little r, end parentheses all squared. It's big R squared minus little r squared. Important detail there. It's the whole area inside the green circle minus the whole area inside the blue circle. Now here I actually see that the green radius is actually always 3. And the blue radius, well, the blue radius is y. So my area as a function of x is pi times 3 squared minus y squared. Again, I need to get this into x, so pi times 9 minus. And what is y squared? So x is square root of y, x squared is y, x to the fourth is y squared. Oops. Now we do need to figure out here, what is my rightmost x? We do need to know that point of intersection. Here's x equals 0. That's where we start accumulating volume. And we stop accumulating volume here. Or when is, oops. So x is square root of y. When y is 3, what is x? x is going to be square root of 3. So my volume is the integral from 0 to root 3 of the cross-sectional area. In this case, it's this annulus, this washer kind of thing. Pi times 9 minus x to the fourth dx. Okay, so this gives me pi times 9x minus 1/5 x to the fifth, evaluated from 0 to root 3. Or pi times 9 root 3 minus 1/5 times, well, root 3 is 3 to the 1/2 power. So that's 3 to the 5/2 power. Or that's going to be pi times 9 root 3 minus 1/5. 3 to the 4/2 power is 3 squared. So that's 9. And then I'm left over with a 3 to the 1/2 root 3. Or this all turns out to be 9 pi times, what is it? 4/5 root 3. Probably could write that a little bit nicer, but not a whole lot nicer. We can make that. One thing to notice about this, because of the kind of wonky relationship between x and y here, that does kind of break. You might be looking at this and saying, wait, don't I have like 4 units of length times 1 unit of length? It's like units of length of the fifth power. Well, because x equals square root of y, the units of length are a little wonky here. So, this, if you were dealing with this in a physics class, figuring out the units would be a problem in and of itself. So I'm going to be a good mathematician here and say we're ignoring units at this point and just working with abstract numbers. So sometimes the units trick works out nicely, but here, because the variables are related to one another a little wonky like this, we would have to really think a little harder about what all the units were here. We would still end up with square units here, but it would kind of be because x, I think its units would be more like square root of length in some sense. Okay. All right. Any questions so far? Okay, so that's the real material for today, and that's what the homework is on, section 6.2. I think maybe we still have a half an hour left, so we'll do a little motivating example for using the shell method, finding volumes using the shell method, and maybe one example, or maybe we'll just work through the motivating example. So let's take a look at this problem. It might seem like we can just find the volume of any solid using the disk or the washer method. And again, in theory, that does work. In practice, though, sometimes it might be a little bit difficult. So the shell method is an alternate method. So let's consider this solid. The solid obtained by rotating r about the y-axis, where r is bounded by y equals sine of x squared from x equals 0 to x equals root pi. And here I see that, well, sine of 0 is 0. Sine of root pi squared as sine of pi is 0. And it turns out this curve looks something along these lines. And I might also, I probably should say, and the curve y equals 0 between these two. So my region is this region here, and I'm rotating about the y-axis. So, okay, no big deal. I mean, I just draw my figure here. When things rotate around, they look like this. My top looks like this. Looks a little bit like a bundt cake pan kind of thing like this, just here it's, 90 degrees. It's tilted back 90 degrees. So no problem. I take my plane perpendicular to y because y is the axis of rotation. I get an inner and outer radius. I mean, okay, that's a little bit annoying, but we just saw how to deal with that. Let's bring this plane down here. Now, one thing that I do notice that's a bit strange is my inner and outer radius or radii actually kind of come from the same function. So I have a radius, say blue little r, and I also have a radius, say blue big R. And my region of interest is, I guess that was green over here. So, oops, my region of interest is the green area in here. So again, no big deal. My area as a function of y is just pi times big R squared minus little r squared. But the question is, well, what are these radii? Right. Um, yeah, there, use red. So these radii are these distances here. But to find these distances, I need to invert y equals sine x squared. Now, if I just had y equals x squared, well, x is like plus or minus root y, no problem. But if I have y equals sine x squared, I really can't solve that for x in terms of y. I mean, I guess I could say that it's like plus or minus the square root of arc sine y, but then we need to like somehow plug that in um, to an integral and do something with that. I mean, what x is plus or minus the square root of arc sine y? Like, what am I going to do with that? And I even have to be careful when I take inverse sine that I do all of that the right way, right. So this is going to be at best very complicated. And I'm going to get an integral of something like arc sine of y. This is not going to be a nice strategy at all. If we can even make it work out, it's going to be very difficult and cumbersome. Right? Integrating arc sine y isn't going to be nice at all. So the question then is, okay, is there another approach? Instead of taking oops, I guess I got to erase a little more. Instead of taking a cross section and integrating cross sections this way, is there another approach I can use? And the answer is, well, nicely enough, yes, there is. We can use the shell method. Let me just get rid of these two. So I really, really want to use this direction, right? I really want to integrate something that's like the integral of y, something that's like the integral of sine of x squared. I really do not want to do anything in this direction. Okay, let's redraw our figure. So again, we have this kind of like, upside down bundt cake pan. And what I might want to do here is instead of taking cross sections and stacking cross sections, um, what I want to do is I want to create shells from an innermost shell and build my solid using, yeah, it's almost like cylindrical cross sections using cylindrical shells. So I don't know if they still do this anymore, but have you ever gone to one of those like old time fairs, like a Renaissance festival or like Pioneer Festival kind of thing? Um, and they do like candle dipping. So you like take just a piece of string and you have like 10 or whatever kids lined up in front of this like pot of molten, paraffin wax, which sounds really dangerous when I think back to it, but I did it as a kid and I don't think anybody ever like burnt their face off or anything. But you go up and you dip your string into the paraffin wax and it like coats the string, and then you walk back to the back of the line and you wait for it, and after 10 seconds, 20 seconds, that layer hardens and you come back up and you dip your string in again and it puts another tiny layer of wax over the previous layer. And you do this like, 50 times, and the parents are happy because the kids are just standing there going around in a circle and not getting into trouble, I guess. And at the end of it, you've put a bunch of layers of wax, in shells around each other and made a little candle. So, right, it's just like the wax kind of builds up from the inside, from that axis of symmetry, that string, all the way out. That's what we're going to kind of do here. We're going to think of building up using using a cylindrical shell, our volume. So we're going to take a little shell like this. I'm going to draw it a little nicer down here. So I have this shell. It's like a little slice of a cylinder. And I'm going to start at the innermost point, where I put a little tiny shell here, and then put one outside of that, and then another one outside of that. And I'm going to build my, uh, importantly, solid of revolution, build it up from the inside, from the axis of revolution or rotation, out uh, towards the outermost shell. I'm going to be using shells of width delta x. I see that the shell height is going to be y equals f of x, as long as I use a shell that has a small delta x. The difference in height between the inside radius and the outside radius should not be substantial. So again, I can get away with making this approximation y equals f of x here. Just like with Riemann sums, right? That approximating the like three-sided rectangle with the curvy top, I can approximate that by just the full rectangle. And as long as I'm taking the limit, everything works out okay. And my radius here, maybe I'll draw this in a different color. My radius here, again, from an inner radius to an outer radius, the difference is only delta x. So my radius here is approximately x for a shell that is over here at x. Now, what I can imagine doing is kind of cutting this little cylindrical piece down one side So like, you have a Coke can with the top and bottom cut off of it, like take your shears and cut up the side of the Coke can and lay it out flat. And what does that give me? That gives me what's essentially a cuboid. Again, not exactly, but in the limit, as n goes to infinity and delta x goes to 0, we'll have this kind of a shape. This will have thickness, delta x. It'll have height, y equals f of x. And it'll have width. The width isn't x. The width is the circumference. It'll have width 2 pi x. Right? Pi times the diameter, or that's pi times twice the radius. So this little chunk of volume, v sub I, is going to be 2 pi x sub I, f of x sub I, delta x, or delta xi if we were using different delta x's. I've got to be really careful here how many of these I add up. I don't want to start adding them here and go over, because then I'd be like adding an outer shell, inner to the middle, and then adding inner back to outer again. I'd actually end up with double the volume. So I start at the innermost shell, the axis of symmetry, and add out. So this is going to go from x equals 0 to root pi. So really, when I take the limit, this is one little chunk of volume. I'm adding up a bunch of chunks of volume, so that's just the sum of the VI's from I equals 1 to n. Let n go to infinity, and we get that the volume is the integral, again, being very careful here, not minus root pi to root pi, but from 0 to root pi, from the innermost axis of symmetry, the innermost shell, to the outermost. And my formula is 2 pi x f of x dx. Or in this case, what is f of x? F of x is sine x squared. Now this might look pretty terrible, 2 pi x f of x, integrating that. On one hand, note that we have units of length for f of x for the height, units of length. So we do have cubic units, that checks out. But actually, this isn't too bad, right? Just the basic substitution. We see that if we pick u equals x squared, du is 2x dx. Hey, there's our 2x dx, works out super nicely. So when u is x squared, when x is 0, u is 0. When x is root pi, u is pi. My pi comes down. My sine of x squared turns into sine of u. And 2x dx turns into a du. I don't know why I'm doing all this in red. It looks like I'm very angry at the problem for some reason. So I have pi, integrate sine of u to negative cos of u from u equals 0 to pi. Or that's negative pi. Cos of pi is negative 1 minus cos of 0 is 1. Or this is negative 2 times 1, or times negative 1 is 2 pi. So this volume should be 2 pi, or around 6-ish. And we could come up here, I suppose, and ask ourselves, okay, square root of pi, square root of 3 is like, about 1.5-ish, maybe like 1.7, 1.8, but 1.5 to 2, somewhere in that ballpark. And the height, of course, is going to be 1. So we could ask ourselves, like, if I had a circle of radius 1.5 to 2, what's going to be the volume of that whole cylinder? We could do something like that to check our work. Um, but we should end up with something significantly bigger than 2 pi and be pretty confident in our solution, but not, 10 or 20 times as big as 2 pi. We should end up with, you know, maybe something about twice as big as 2 pi, somewhere along there. So what's the idea of cylindrical shells? We can also compute the volume of a solid using this formula. And our A to B of 2 pi xf of x dx. Importantly, only when it's a solid of rotation or revolution, this disk or, geez, scrolling all the way back up, there we go. This disk or washer method, uh, works for lots of different solids, right? This doesn't have to be a solid of rotation. This formula works very nicely if it's a solid of rotation, but it doesn't really have to be. But for the shell method, it really only works nicely if it's a solid of rotation. So number one, and number two, being very careful about your upper and lower bounds. It's super tempting to say grab these as A and B, but really you'd be adding outer shells all the way to inner and then inner back to outer. You'd be adding up twice the volume instead of just one of it. So we want to go from the innermost shell outwards. So basically from the axis of symmetry outwards in a problem like this, or if we had in another example, maybe a curve that ended here at say 1 and there was just nothing in here, then we want to integrate from say 1 to square root of pi and also not from say 0 to square root of pi. So we have to be a little more cognizant of what bounds we're using. It's a little less clear what upper and lower bound to use than in the disk or washer method. So that is the shell method. Again, no homework questions on the shell method, but figured I would introduce it since we had the time, and gives you a different method of computing volumes. So if you're interested in it, you can try some of the 6.2 problems with the shell method, and probably most of them will work with the shell method, I would think. But if you try one and can't get it to work or something, just email me and let me know. They're not set up for that necessarily, so you could end up with an integral that's not really feasible to do. Any questions on 6.2 volumes or on the shell method? All right, then let me stop the recording.